Welcome everyone to The Explainer. Today we're diving headfirst into what might genuinely be the greatest unsolved mystery in modern astrophysics. We're talking about the ultimate cosmic detective story, the hunt for the origins of ultra-high-energy cosmic rays. These are, without a doubt, the most energetic subatomic particles ever observed in nature. Things that exist, but honestly, according to some of our own models, maybe shouldn't. So strap in, because we're going to track down particles that hit our atmosphere with a force that completely defies human comprehension.
Just listen to this quote. "I thought there must have been a mistake." I mean, that was the actual, literal reaction of Toshihiro Fujii, an associate professor who helped discover a particle so extraordinarily powerful that he initially assumed his equipment was just broken. He ended up calling it the Amaterasu particle, named after the Japanese sun goddess. And his shock, it perfectly captures what scientists have been feeling for decades now. We are dealing with an energy level completely unprecedented in nature, one that really forces us to question what exactly is out there in the dark.
Okay, let's dive into this. Chapter 1. The Incident, a Cosmic Anomaly. Every good detective story starts with an inciting incident, right? A crime scene that breaks all the established rules. And for astrophysics, that scene was set back in the early 90s, fundamentally changing our understanding of what the universe is capable of throwing at us. On October 15, 1991, an experiment in Utah detected a particle that absolutely shattered the scales. Physicists literally dubbed it the "oh my god" particle. It arrived with a mind-bending energy of 320 ex-electron volts. To put that completely wild number into perspective, this single microscopic particle was traveling at, well, 0.999. Actually, scratch that. It's 23 nines and then a 57, times the speed of light. If a photon, a literal particle of light, raced alongside it, it would take over 245,000 years for that photon to pull ahead by just one single centimeter.
The sheer physical impact of these things is what's truly mind-boggling. Take the Amaterasu particle, which was discovered more recently, at 240 exa-electron volts. We are talking about a microscopic, subatomic speck hitting Earth's atmosphere with the macroscopic kinetic energy of a fast-moving tennis ball, or, a baseball traveling at 72 kilometers per hour. Just imagine taking all the momentum of a thrown baseball and packing the whole shebang into a single proton or atomic nucleus. It's almost unimaginable.
Chapter 2. The Evidence. Analyzing the particles.
So, what exactly are these mysterious intruders? If we're going to track down where they come from, we first need to analyze the physical evidence. We need to know what they're made of. By definition, an ultra-high-energy cosmic ray, or UHECR, is a subatomic particle arriving from space with kinetic energy exceeding 1 exa-electron volt. At these extreme scales, we're looking at center-of-mass collision energies hundreds of times greater than anything we can produce on Earth. The Large Hadron Collider, the absolute most powerful machine humanity has ever built, is roughly 10 million times less energetic than these cosmic anomalies. Our planet is basically sitting in a natural laboratory far more powerful than anything we can even dream of engineering.
Now, a really crucial point here is the mass composition of these particles. While lower energy cosmic rays are mostly just single protons, the highest energy ones are a totally different story. Recent studies suggest a significant fraction, maybe 30% or more, are heavy ions like iron, or even ultra-heavy elements like selenium, tellurium, and platinum. These ultra-heavy nuclei can only be synthesized in incredibly violent, neutron-rich environments. The fact that we are seeing them hit Earth means they survived an unbelievably brutal journey across the cosmos.
Chapter 3. Forensics. Catching the intruders. But how do we actually catch them? That brings us to our forensic methods. Because here's the catch. At the highest energies, maybe only one of these particles strikes a single square kilometer of Earth per century. You can't exactly just set out a bucket and hope to catch one, right? Instead, we use the Earth itself. When a primary UHECR slams into an atmospheric molecule, it shatters, triggering this massive cascade called an extensive air shower. Our atmosphere acts as a giant calorimeter. That single primary particle creates a downpour of billions of secondary particles, like muons and electrons, spreading over miles. We catch them by building giant observatories covering hundreds or even thousands of square kilometers on the ground, just waiting for that vast secondary footprint to wash over our detectors.
And this brilliantly illustrates how we actually find these hotspots. Observatories like the Pierre Auger Observatory in Argentina and the Telescope Array in Utah map out the arrival directions of these air showers. Over decades, they compile these huge sky maps, searching for hotspots, areas where slightly more of these extreme particles seem to originate. It's painstaking work, just a slow accumulation of breadcrumbs pointing back out into the dark.
Chapter 4. Physics Laws. The cosmic speed limit.
But our investigation hits a massive roadblock here. There's an ultimate cosmic speed limit that severely complicates our search and drastically shrinks our suspect pool. It's called the Greason-Zatsepin-Kuzmin limit, or just the GZK cutoff for short. As these ultra-high energy particles travel across millions of light years, space isn't actually empty. It's filled with the cosmic microwave background, the leftover radiation from the Big Bang. When a particle travels fast enough, those low-energy photons act like a thick fog of friction. The particles inevitably collide with the photons, lose energy, and drop below the extreme energy thresholds we observe.
Because of this GZK cutoff, any particle we detect with energy above 50 ex-electron-volts simply could not have traveled from the distant edges of the universe. It absolutely would have lost its energy along the way. This means the highest energy particles must originate relatively close by, within our local cosmic neighborhood, say roughly a few dozen megaparsecs. In short, our suspects have to be local.
Chapter 5. The Suspects. Profiling Accelerators.
So, who in our local neighborhood is capable of firing these subatomic bullets? It's time to profile the incredibly violent astrophysical accelerators that could theoretically act as the gun. Things that we normally think of as super energetic, like standard supernova explosions, they actually aren't powerful enough. To reach these insane energies, we need the most extreme phenomena in the universe. We're looking at feeding supermassive black holes, collisions between dense neutron stars, cataclysmic gamma-ray bursts, highly magnetized stars called magnetars, and vast radio galaxies.
Vast entities like radio galaxies are prime suspects. In the vicinity of supermassive black holes at their centers, matter is literally stripped down to its subatomic structures. Immense magnetic fields confine the protons and heavy nuclei, trapping them in powerful shock waves that continuously bounce them back and forth. This accelerates them closer and closer to the speed of light before they are finally hurled out into the intergalactic void.
But accelerating a particle to this level requires a delicate and, frankly, almost impossible balance of plasma physics. The source has to be large enough, and its magnetic field strong enough to confine the particle during acceleration. Simultaneously, the process can't be so violently dense that the particle loses all its energy to radiation before it even escapes. Only a tiny, tiny fraction of cosmic objects hit this precise physical sweet spot.
Chapter 6. Mystery. The Cold Case Files.
So, despite having a list of suspects and a basic understanding of the weapon, tracing a specific particle back to its exact source remains one of astrophysics' biggest challenges. Welcome to the Cold Case Files. The fundamental problem here is that UHCERs are charged particles. Unlike light, which travels in a nice, straight line, charged particles are bent and deflected by the magnetic fields that permeate galaxies and intergalactic space. By the time an ultra-high-energy cosmic ray reaches Earth, its trajectory has been warped and twisted through a giant cosmic magnetic maze. The universe effectively wipes the fingerprints right off the arrival directions, blinding us to their true origins.
Which brings us to the most frustrating clue of all. When scientists tried to trace the trajectory of the Amaterasu particle backward, accounting for those magnetic deflections, it didn't point to a supermassive black hole. It didn't point to a massive radio galaxy. It pointed to an empty region of space, a cosmic void. There are literally no known massive galaxies or astrophysical accelerators in that direction. It's as if the particle materialized out of absolutely nowhere.
And this leaves us with a truly profound question. If our current maps and models can't explain the origins or the trajectories of these incredibly energetic particles, are we missing something fundamental? Could these impossible particles be defying the GZK cutoff? Could they be decaying from super heavy dark matter particles left over from the Big Bang? Today, we're pushing deeper into the emerging field of multi-messenger astronomy, looking at cosmic rays, neutrinos, and gamma rays, all together to map the most extreme environments in the universe. But right now, we have to wonder if these cosmic rays aren't just astrophysical events, but actual messengers from a totally undiscovered realm of physics beyond the standard model. So what do you think is hiding out there in the dark?